Every second, the world creates billions of data points. A tweet, a sensor reading, a credit card swipe. How do companies turn that endless flow into instant insight? In the next few minutes, we will demystify how data stream processing is used to do this. And we'll see how the next generation self-adaptive data stream processing are trying to make processing smarter, faster, and more resilient. No expertise is required, just curiosity. In the real world, some types of data, like stock market data, are constantly being generated. This data can be thought of as a continuous stream flowing in from various sources. To help illustrate this concept, imagine a data stream as a river. Just like a river, a data stream flows continuously, always in motion, never static. And just as a river seems to have no end, a data stream can be thought of as a never-ending with no definite endpoint. So what exactly is data stream? Simply put, it's an ordered or unordered sequence of events that has potentially no bounds and is infinite. Think of it as a constant flow of information, with each event carrying a tiny piece of data. For example, an event arising from transaction might include a timestamp indicating when the transaction took place, the type of transaction, and the amount involved. Similarly, a sensor might generate an event with a timestamp, sensor ID, and the temperature reading. Each of these events is like a small droplet of water in the river, carrying a specific piece of information that contributes to the overall flow of the data. Now that we have explored the concept of data streams, let's talk about how we can process this constant flow of information. To illustrate the different approaches, let's go back to our river analogy. Just as a dam can be used to store water from a river and generate electricity later, we can collect and store data from a stream and process it in batches. This is known as batch processing. On the other hand, we can also use the water from the river to generate electricity or power a mill instantly, without storing it first. Similarly, we can process the data stream as soon as it arrives without storing it. And this approach is called as data stream processing or stream processing. So, how does stream processing compares to a batch processing? One key advantage is that results are obtained in almost real time, allowing for quick decision and rapid reactions. For example, in trading, every second counts, and stream processing enables this instant responses to changing market conditions. Similarly, in safety system, stream processing can help detecting and responding to potential hazards in real time, making it a critical component of many industrial applications. Another benefit of stream processing is that it doesn't require storage before processing, which means that we can handle unlimited amount of data without ever storing it. Stream processing transformations are relatively simple when compared to batch processing to keep the low latency requirements. But this difference is getting lower and lower as frameworks are becoming more and more mature. Hence, stream processing plays a particularly important role in applications where seconds or minutes can make the difference between profit and loss or safety and danger. Data stream processing is characterized by high velocity and high volume, which translates to high throughput and very low latency. Throughput is the rate at which an event is generated or processed, while latency refers to the amount of time it takes for an event to travel from one point to another. In the context of data stream processing, it typically lies in the range of milliseconds to seconds. These two metrics are critical factors in determining the overall performance of our stream processing systems. Let's unpack what goes under the hood of a data stream processing system. A typical data stream processing pipeline consists of three main layers: the source layer, the processing layer, and the sink layer. A directed acyclic graph, or DAG, can be used to model the data flow across these layers, which shows how information moves from one stage to next. The DAG has nodes, which represents different functionalities, and has edges, which represent the intermediate streams of data. The term directed means that data flows in one direction, and acyclic means that there are no loops. Looking at the DAG, we can see that data arrives from source, which can be anything, a sensor to a website click event or an online event transaction. This data is then processed using various algorithms, and the processed data is sent to a sink, which can be a database, a real-time dashboard, or further downstream processing tasks. Now let's take a closer look at processing part of the pipeline. In data stream processing, the fundamental computational unit that performs and actions on incoming streams is called an operator. Operator consists of different types of processing, including transformation, filter, joining, and stateful operations. There are different types of transformation operators, such as map transformation, which applies an operation to each event and produces one output for each input event. For example, converting degree Celsius to degree Fahrenheit. There is also a flat map, which applies an operation to each event and can produce 0, 1 or more outputs for each input event. We also have filter operators, which filter input event streams, and stateful operators, which keep track of the current state of the counter or variable. Additionally, there are joining operators that perform joining operations on multiple data streams to enrich the information of incoming data. Window operators perform computations like summing or averaging over a subset of data streams. The subset of data streams can be created using different kinds of windows, including tumbling windows, sliding windows, and session windows. Each of these windows is characterized by how the window size is defined. These are the core concepts that make up a data stream processing system. By understanding these building blocks, we can design and implement data stream processing pipelines. Let's now see how these pipelines are implemented in real world using a concrete example. Imagine we are the IT systems team for a bank and we want to track credit card transaction to detect fraudulent activity and alert our customers. A typical data stream processing pipeline for this use case would involve several components. First, we have various data sources such as payment gateways, bank core system, mobile wallets, e-commerce platforms, ATMs, and trading platforms. Each of these sources generates an event for every transaction, which can include information like timestamp, transaction ID, user ID, amount, and location. These events are then sent to message queuing system like Apache Kafka, which acts as a buffer and helps decouple the data sources from the data processing layer. The data processing system then pulls the data from the message queuing system. Various open source frameworks like Apache Flink, Apache Spark, structured streaming, or Apache Kafka streams can be used to process incoming data streams. Using particular logic or algorithms, these frameworks can detect fraudulent transactions. If a fraudulent transaction is detected, for example, for consecutively high transaction, an alert is generated, and this alert is then forwarded via a message queuing system to the sink. The sink can be a bank's notification system, forwarding the notification to the user. These processes typically run on dedicated infrastructure, which can be a cloud system, on-premise system, or even a high-performance computing system. The amount of resources required depends on the incoming data volume and the complexity of the processing. For a simple use case, a simple setup might be sufficient, but as the number of users grows, we need more and more processing power. And that's where scaling comes into the picture. We can scale up by adding more resources or CPUs to a single machine or single node, or we can scale out by adding more nodes and more machines with multiple resources. Scaling out results in computing paradigm known as distributed computing, where we distribute the computation across multiple machines or nodes. Such kind of computing also provides fault tolerance, which means that if one node fails, the computation continues on other available machines without losing any data. Most data stream processing frameworks can scale up as well as scale out. However, setting up and configuring this system requires some domain knowledge and experience. Various parameters and settings like parallelism factor, number of workers, window sizes, memory allocation, etc. need to be configured depending upon the data, processing complexity, and infrastructure. Once the system is set up and deployed, it is expected that everything will run smoothly, but in reality, streams can be messy and challenging to handle. We face issues like massive volume with millions of events per second requiring huge parallelism and efficient networking. We also encounter velocity challenges where sudden increase in traffic like during Black Friday sales require additional resources in a short amount of time, and then need to scale down once the event is over. And finally, we need to ensure low latency with millisecond level alerts requiring quick rebalancing and tuning. These challenges can prevent the data stream processing system from running efficiently. And that's where the need for self-adaptive mechanisms to handle data stream processing system come in. Self-adaptive mechanism adds an intelligent autonomous layer on the top of the data stream processing system, one that monitors, analyzes, plans, and executes adjustments on its own, using the knowledge it continuously gathers. The process begins with monitoring. Here, the system observes key performance metrics like input throughput, latency, CPU load, memory utilization, etc. These values are constantly collected from both the systems and its environment, forming the foundation for decision making. Next, the analyzer component interprets these metrics to understand what's happening. For assessing the situation, it can either use simple rule-based logic, where predefined conditions trigger actions. For instance, if latency exceeds a threshold, detect the performance degradation and create an alert. Or through machine learning models, where time series forecasting or other predictive methods can help in predicting upcoming changes and performance degradations. Then comes the planner. Based on the analyzer's insights and system's objectives, it formulates an adaptation strategy to bring the system to desirable state. For example, if high latency is detected and an alert is created, it increases the parallelism to a certain value. This stage transforms the analysis into concrete actionable steps. Finally, the executor carries out those actions in real time. This could involve elastic scaling, such as adjusting the parallelism factor or starting and stopping multiple machines, or dynamic reconfiguration like tuning window sizes or checkpoint intervals. All these components share a common knowledge base, a central memory that stores system data, learned experiences, and operational policies. Together, they form so-called the MAPEK loop: monitor, analyze, plan, execute, all revolving around shared knowledge, and the most powerful part, the entire loop runs continuously and autonomously. The system adapts itself without a single button press or a manual tuning from a human. Let's put the adaptation loop to the test with a real-world problem. We'll continue with our example of detecting fraud in credit card transaction. Imagine a scenario where the service must flag suspicious activity within mere 100 milliseconds of the purchase, even when the traffic surges during peak events like Black Friday sales or flash sales. The objective is clear: maintain latency no matter what, by either scaling up or scaling out. On a typical day, the system hums along as usual, but behind the scenes, the self-adaptive mechanism is hard at work, monitoring and analyzing key metrics like input throughput and latency. Then the flash sales day arrives, and the transaction volume skyrockets. Latency increases and the monitoring component springs into action, sending metric information to the analyzer. The analyzer evaluates the monitoring data and determines that the system is unable to maintain the latency below objective, that is 100 milliseconds. It triggers the performance degradation alert based on the defined objective. The planner then decides what changes needs to be done in order to reduce the latency and make the data stream processing system stable again. Here, for example, planner decides to add 2 more CPUs to the processing pipeline, increasing parallelism factor to 3, each hosting replica of the fraud detection logic. The planner submits the plan to the executor component, which launches new processes with additional CPUs. The data stream processing framework detects these changes and rebalances the incoming data accordingly. As a result, latency drops below required threshold and the system is once again operating within the acceptable parameters. But that's not all. All of this information is saved in knowledge database, which serves as a reference point for all the components to take the actions in the future. These database also enables predictive scaling, allowing the system to anticipate and prepare for future surges in traffic. By leveraging the adaptation loop, our system can respond quickly and effectively to changing conditions, ensuring that latency remains low and performance remains high, even in the face of unexpected spikes in traffic. Across diverse domains from finance and gaming to transportation and media, self-adaptive systems are transforming data stream processing, making it more efficient and resilient. It all began with a simple idea, a foundation built to tackle the challenge of big data flowing in continuous streams. With each evolution, data stream processing grew stronger, more flexible, and increasingly aligned with the demands of modern development. And now, we have entered currently in the third generation of data stream processing, an era defined by serverless computing and intelligent orchestration, where data stream processing systems can monitor, optimize, and adjust themselves automatically and autonomously, becoming more autonomous, resilient, and efficient than ever before. In this lecture, we explored what data streams are and how they are processed through key foundational concepts. We also discussed how self-adaptive mechanisms play a vital role in making data streams processing more efficient and intelligent. As we move forward, this idea will continue to shape the next generation of real-time data systems. Thank you for watching and happy streaming.